okay, with these examples, we are then led to the final part of this lecture about, okay, these were the bad examples. What can you then say? And certainly one might get a certain sense of panic that, okay, everything goes wrong. But usually in math, what happens is that, okay, for naive statements, you have counterexamples. But with further thought, you can add assumptions that will salvage these theorems and make real statements. So I'll state first these theorems, and we'll see how much time we have to prove. I think we'll have time for the integrals. So first, yeah, with integrals. And if you have fn continuous, and these are converging uniformly to a function f, then the limit function is Riemann integrable, and this is permitted. So uniform convergence saves you. And a crucial thing here is also bounded interval. This precludes, say, examples like the one we saw with the moving wave. The moving wave itself, as I presented, was not uniformly convergent, but you could, without that assumption, get an example. So there are two parts of this that are important: bounded interval and uniformity. These permit that fact. And there is another way of interpreting this. You don't have to understand this, but if you like, I have talked a lot about this space of continuous functions with the uniform norm. This came up last week when we stated that this space is complete. So it's functions f on some interval that are continuous. Now, if you equipped it with the uniform metric, then it's complete, but you can also say other things. If you can define a functional on this space given by the integral of f, and this function I of f is continuous. And the proof is, one of the proofs, you can do other things, is that this is sequentially continuous by the above. In your homework, you actually proved this in a different way. You proved it directly with an epsilon delta proof. But this statement can be thought of as saying that the integral is sequentially continuous. Because what is this? This is limit of I of fn. And this here you have I of the limit of fn. And you're just saying that these are the same. So you're passing the limit inside the interval. With uniform convergence, that is permitted. And that's okay. You can strengthen this assumption theorem quite a bit, and I won't. But in this class, we don't need that. And actually, for applications, I can say by experience that maybe 70% of 80% of the time, even in relatively advanced mathematics, the previous theorem is enough. So you don't need much fancier tools than that. At least say 70–80% of the time. There are fancier tools, but they are usually not as, they have more niche applications. Okay, but what about derivatives? Uniform convergence was not enough. And with derivatives, we have to be a little bit careful with the domain. So for technical reasons, I will stay, to avoid issues with the endpoints, I will say that we have an open interval. Now, you could state this with a closed interval AB as well, but in 131A, we didn't define differentiability at an endpoint. So you have to exclude the endpoints somehow, and then you'd have to say continuity at the endpoints. It's just annoying. So I'd rather assume that you have an open interval to avoid these technicalities. You may find statements where it's done slightly differently, and the proofs are the same, except maybe worrying about the endpoints slightly. But okay, we have to assume then that fn is differentiable, because we cannot talk about derivatives without that. And we have to assume that some convergence, this time pointwise convergence, is enough, except that we need two additional assumptions. Well, we need that the derivatives are continuous. Technically speaking, you can do with less again, but this is to ensure that certain integrals are defined. And we need another assumption that the derivatives converge uniformly to some function g. We cannot say that they converge uniformly to f prime of x because we are trying to conclude also that f is differentiable. So we are assuming some other function g. Then we can say that f is differentiable and the derivative is equal to g. That is, f's derivative, the derivative of the limit is equal to the derivative, the limit of the derivatives. So 3 assumptions: pointwise convergence, the derivatives are continuous, and the derivatives are converging very nicely. So if you go, it's an instructive example to, after this lecture, say at some point, go over examples that we gave and see which of these assumptions fail. Usually it is either the continuity, well, the in those examples, all the derivatives were continuous, but it is this assumption B that fails in the ones that I gave. Okay, any questions on the statements or? Okay, so I think we have time to go over this proof with the integrals. It's actually not very difficult, and it's very similar to what you did on your homework, homework number 4, I believe, the one talking about 3, I mean, about continuity. So we want to prove this theorem, and it has 2 claims: that the limit function is Riemann integrable, and that you can exchange the orders of integrals and limits. Now, okay, we have to prove this, so there's always in your proofs a setup. We suppose that Fn is a sequence of continuous functions that converge uniformly to some function. Now, first, integrability. This is actually a very short thing. What can we say about the limit function f? By theorem from Wednesday, and this f is continuous since it's a uniform limit of continuous functions. And don't worry, we don't need a lot of Riemann integrability stuff from 131a. I know that that is something that's not always covered very carefully, and it's a difficult topic of 131a. So you don't need a whole lot of it in this class, but you need the following fact for this proof that you can assume is that by a theorem from 131a, continuous functions are integrable. So f is integrable. We need to state this just like with the soups and limits because we have to make sure that the integral is actually well defined. Okay, now all the integrals in this problem are well defined. Also, technically Fn's integral is defined because it's continuous by the same argument. So now we want to prove that the convergence that we had. So let's fix an epsilon. We have to use the uniform convergence somehow. So there exists an n such that for if n is bigger than or equal to n, then for all x in the interval of interest, we have that Fn of x minus f of x is less than or equal to epsilon. Okay, we have to choose an n. Now this claim says that there exists an n, so let's emphasize that we choose now such an n, and let n be bigger than or equal to n. And we want to conclude the convergence, argue the convergence, so we have to estimate. So let's estimate the integral. So we are saying that the limit of the integrals is converging to the integral of the limit. So we have to estimate the difference between these two things. And okay, we put them in the same integral, just like you did, at least probably most of you did in your homework. Fn of x minus f of x dx. You pull the absolute values inside by the triangle inequality. And again, this is using facts from 131a that you can assume. Of course, it's good if you know the proof of them. And now, again, now by star, we have that the integrand here is less than or equal to epsilon. So if the integrand is always less than or equal to something, then the integral is less than or equal to the integral of that something. In this case, this is a constant. So what we get is epsilon b minus a. And okay, this shows that our choice of here we want to choose a little bit better to get the point through. So let's choose epsilon, edit this a little bit to make it epsilon over b minus a. And this way we can absorb the constant at the end. So we can add a b minus a there, b minus a. And we get that the upper bound of epsilon. So for every n, for every epsilon, we found an n that would work. We had to modify the bound a little bit in the uniform convergence. Okay, I think this is good for today. I don't want to go to the derivative proof. If you have any questions, I'll stick around. And the only thing I will say about the derivative proof now is that it is a consequence of this integral proof, and it involves the fundamental theorem of calculus. So if you want, you can review a little bit fundamental theorem of calculus for next time, or you can look at the sketch. I will start Wednesday's lecture by doing the proof of the other theorem, this theorem about derivatives. There's a sketch here, you can look, but it's a consequence of the integral fact. So thanks, and feel free to ask any questions if you have.